In this video, we're going to quantify solubility, taking it beyond the qualitative realm of soluble or insoluble. We're going to see that solubility is a continuum, and in particular, we can characterize how soluble a solute is in quantitative terms using the solubility product constant KSP, which is just a special type of equilibrium constant. It's an equilibrium constant in particular for solubility equilibria, such as the ionic solubility equilibrium that we saw in the last video between a hypothetical salt AB and dissolved A plus cations and B minus. All the tools of equilibrium that we've already learned apply just as well to this solubility equilibrium. But we're going to notice some interesting things about this, in particular the fact that the reactants do not appear at all in the equilibrium expression, and the idea of back calculating the initial amount of dissolved solid given equilibrium concentrations of A plus and B minus. So how do we quantify solubility? Well, as a first pass, we might think about the idea of using moles as a quantifier of solubility. How many moles of a solute can I fit in solution, can I dissolve in solution, until I start, for example, adding solid and more solid won't dissolve? The problem with that is that empirical experience tells us that the more liquid solvent we have, the more solute molecules we can fit in solution. So the problem with this is that it's extensive with respect to the solvent, which means that we can't use the moles of solute without information about the liters of solvent, for example, we're talking about. What this suggests is if we take that number of moles and simply divide by the liters of solution, now we have an intensive measure of solubility that is intrinsic to a solute at a particular temperature and pressure. In general, the dissolved moles of solute per liter of solution is limited. That's to say, only a finite amount of solute can dissolve in 1 liter of solution, and there is some number in moles per liter that we can pin to a particular solute to describe its solubility in quantitative terms. How many moles, how many particles of that solute can we dissolve in a liter of solution? This is how we define solubility in quantitative terms. It's defined as the maximum molarity achievable for a given solute dissolved in a given solvent. Think back to the strontium phosphate case. We saw that there was a solid mass at the bottom of the beaker, and even though particles were constantly entering and leaving the solid and dissolved phases, the total molarity of strontium and phosphate in solution was constant. And that's true even if we added more strontium phosphate. That would just lead to more solid piling up at the bottom of the beaker. There is a maximum molarity achievable for that solute. That's what we define as the solubility. We alluded to this last time, but just to remind us, remember there's no such thing as perfectly insoluble. That means that the solubility of a solute, let's call it M, is necessarily greater than 0 moles per liter. All solutes are soluble in all solvents to some degree. We now know how to quantify solubility by thinking about the maximum number of moles of a solute that can dissolve in a particular solution. Now that we know that, we can begin to apply our general picture of chemical equilibrium to solubility equilibria as a particular context. And so, in solving solubility equilibria problems, just as we saw for chemical equilibrium problems in general, the first step is to write the balanced chemical equation. And the way we tend to do this, just by convention, is to write the reaction in the direction of dissolution and write an expression for Kc. When we write the reaction in the direction of dissolution like this, by convention we are writing it such that the equilibrium constant is equal to Ksp. And note that when we write this equilibrium expression, that the reactant, the solid solute, is a pure substance. So it doesn't appear in the equilibrium expression. Only the products appear in the equilibrium expression. In this case, the separated aqueous ions A plus and B minus. This is true for all equilibrium expressions for solubility equilibria. Products only appear in the expression for Ksp. The stoichiometric coefficients may not be 1, and so we need to remember, as usual, to raise each concentration to its corresponding stoichiometric coefficient. This is a typical equilibrium expression. There's nothing odd here except for the fact that none of the reactants appear in the equilibrium expression. So Ksp has no denominator. And actually this turns out to be a virtue in many cases. It simplifies our problem a lot of the time. We call Kc the solubility product constant, Ksp. There's nothing too special about Ksp except that it applies exclusively to dissolution equilibria like this. Intuitively, what is a large KSP telling us? Well, as we saw before, a larger value of K indicates that products are favored. That means a large KSP corresponds to greater solubility, larger concentrations of the dissolved ions A plus and B minus at equilibrium. Ultimately, because all of the dissolved ions must have come from solid starting material, we can trace this back to more moles per liter of the starting solid dissolved in solution. This kind of begs the question, though. We know how to, for example, calculate equilibrium concentrations of A plus and B minus given initial conditions in a KSP, but how can we find the solubility of the solid, say AMBN in the general case where there's more than one cation and one anion in the salt, if it doesn't appear in the equilibrium expression? If we were to do an ice table, for example, and solve for equilibrium concentrations, the solid would disappear from solving that problem since it's a pure solid and doesn't appear in the equilibrium expression. How can we find the solubility of the solid if it doesn't appear in the equilibrium expression? The answer is we can just use stoichiometry, right? If we know, for example, that the equilibrium concentration of A plus is some value, let's say that we know by solving an equilibrium problem that the equilibrium concentration of A plus is A plus EQ. Since all of those A plus cations must have come from dissolution of AMBN, in fact, let's change this up a little bit and write this as A to the A, B to the B to make this a little more clear. That means that the number of moles of AABB that must have dissolved is that equilibrium concentration divided by the stoichiometric coefficient. Say, for example, we were thinking about lithium phosphate here. Since 3 lithiums come from each lithium phosphate molecule, the number of moles of lithium phosphate per liter of solution that dissolved would just be the concentration of Li plus divided by 3. So the answer here ultimately is to use stoichiometry, which we can of course still do, even though the solid doesn't appear in the equilibrium expression, just by thinking about how many pure solute particles it took to generate the dissolved solute particles. So solubility equilibria are interesting because the pure solute, the reactant, does not appear in the equilibrium expression. Only the dissolved solute particles appear. This raises an interesting question from the perspective of Le Chatelier's principle. Let's say we wanted to, for example, shove more dissolved particles into a solution that was already saturated, that is to say, already had the theoretical maximum number of moles of particles dissolved within it. Could we simply add more solid to the mixture to do this? Thinking in terms of a Le Chatelier's principle idea, right? Thinking in terms of, well, if we add more solid, that's going to drive this equilibrium towards A plus and B minus, since we're adding a reactant, and that's going to push the reaction to the right. Will this work from a Le Chatelier's principle perspective? Well, the equilibrium expression tells us that no, this will not work. Reason being, when we add more solid, Q does not change. The reaction quotient does not change upon the addition of additional solid, and we would still be in a situation where Q equals K. The only way to influence this position of equilibrium, in fact, is to somehow remove solute particles through precipitation. We could, for example, use a different anion to precipitate some of the cations out of solution to influence this equilibrium. But we can't simply add more solid to drive the solubility higher. We could also ask the same question about removing pure solid from the bottom. Could we cause additional precipitation if, for example, we scooped out some of this precipitate? The answer there is also no. Removing the pure solute will not cause additional precipitation because, again, we can't remove solid AB and expect the reaction to run backwards. Again, Q does not change since the concentration of solid AB does not appear in the expression for Q. Q remains equal to K, and the system remains in equilibrium. Let's look at a couple of examples now of calculating molar solubility of a salt from its KSP and KSP from a given molar solubility value. So let's start with calcium hydroxide. KSP for calcium hydroxide, CaOH2, is 8 times 10 to the negative 6. What is the molar solubility of CaOH2? Well, first of all, let's clarify what this problem is actually asking for. It's asking us for the moles per liter of this salt, of CaOH2, that we can dissolve into solution. we're going to have to do some stoichiometry to work backwards from equilibrium concentrations of the solvated ions back to the molar solubility of the entire salt, CaOH2. The first step is to write a balanced equation for dissolution. And in cases like this, doing this properly is very important. The salt initially is calcium hydroxide, and it's a solid in the normal state. When it dissolves, it forms aqueous Ca2+ and 2 hydroxide anions, which are also aqueous. Note the stoichiometry. We started with 2 hydroxides in the salt, and we end on the product side with 2 hydroxides. The next step is to set up a rice table, plug into the equilibrium expression those concentrations from the equilibrium line, and then solve for what you need to know. So I'm going to rewrite the balanced chemical equation for this dissolution reaction down here, and I am going to include the reactant just so we're reminded of the stoichiometry, even though we know from the phase of the reactant that it won't appear in the equilibrium expression. We'll need the stoichiometry in calculating the molar solubility, as we'll see. We've got initial, change, and equilibrium lines in our ice table, and now we kind of reach an impasse, because it's a little bit unclear what to write on the initial line. How can we envision, how can we conceive this process? One thing we can do right away is ignore CaOH2 solid. It's a solid, it won't appear in the equilibrium expression, and so all 3 cells in this column we can just draw lines through. How do we think about Ca2+ and hydroxide though? Well, let's imagine that we had enough solid in our system to completely saturate, say, a liter of water. We had enough solid in the bottom such that the solution above was completely saturated. What we want to know is the concentrations of calcium and hydroxide in that completely saturated solution. One way to think about this is to imagine the initial state as having no dissolved solute at all. And if we have an excess of solute in the bottom, the question is, what will the concentrations be at equilibrium? So let's think about this situation. Initially, we have no calcium 2+ and no hydroxide dissolved. Hence, we will certainly be going to more calcium and more hydroxide. However, we need to be careful, because for every 1 molecule of calcium hydroxide that dissolves, we get 1 dissolved Ca2+ ion and 2 dissolved hydroxide ions. We still need to respect the stoichiometry in the balanced chemical equation when writing on the change line. Finally, on the equilibrium line, we can write positive X for the concentration of Ca2+ and 2X for the concentration of hydroxide. Now let's plug into the equilibrium expression. In this case, Ksp is going to be equal to the concentration of Ca2+ at equilibrium times the concentration of hydroxide at equilibrium squared. And here's where things get somewhat fun. From the equilibrium line, we know that X is simply equal to the calcium 2+ concentration. The hydroxide concentration, however, is equal to 2X. And so when solving for X, we need to be careful. This equilibrium expression is equal to X times the quantity 2X squared, which on the whole is equal to 4X cubed. Ultimately then, we're solving the equation 4X cubed is equal to 8.0 times 10 to the negative 6. Doing some algebra, we arrive at X is equal to 0.0126 moles per liter. And this is the concentration of calcium 2+ at equilibrium. Are we done? Is this equal to the number of moles of CaOH2 that we can dissolve in a liter of solution? Well, in this particular case, since the molar ratio of CaOH2 to Ca2+ turns out to be 1:1, as it happens, we are done, and this is simply equal to, we can imagine, the concentration of CaOH2 in solution. So the 0.0126 moles per liter is in fact the molar solubility, and we're done. It is important, though, to check that the X value you arrive at is numerically equal to the molarity of the starting solid salt dissolved in solution. We can also do this kind of problem in reverse, starting with a molar or a mass solubility value and working backwards to Ksp. The basic process is very similar. The first step is to write a balanced chemical equation for dissolution in particular. Then we set up a rice table, plug into the equilibrium expression what we know, which in this case we're going to know the extent of reaction. We're going to know the number of reaction events that occurs since we're given the moles of CaF2 dissolved in a fully saturated solution. And then we're going to solve for what we want to know, which in this case is KSP, simply by plugging in those known concentrations into the equilibrium expression. This problem nicely illustrates that it's important in solubility problems to get to mole land as quickly as possible. One thing we should notice is that the solubility here is given in terms of mass of the solute per liter rather than moles. So the first step here is to convert to a value in moles. To go from a mass solubility to a molar solubility, we need to divide by the molar mass of the solute, CaF2, which in this case is about 78 grams per mole. And this gets us to a molar solubility value of 3.317 times 10 to the negative 4 moles per liter. That's going to be an important input into our ice table. So I'm just going to reproduce that underneath the mass solubility up here. We found that this was equivalent to 3.317 times 10 to the negative 4 moles per liter of CaF2 that we're able to dissolve in solution. And it's important to note what we're actually talking about here, because for each mole, for example, of CaF2 dissolved, we get 1 mole of calcium 2 plus ions and 2 moles of F minus ions. So let's start there. Let's start with the balanced chemical equation for this process. We start with solid CaF2. There's an equilibrium between this and the solvated and separated ions, Ca2 plus, which is aqueous, and F minus, which is also aqueous. And there should be a stoichiometric coefficient of 2 in front of the fluoride to ensure that the equation is balanced. Now let's think about the ice table. Initial, change, and equilibrium lines. It might seem a little bit unclear, given the way this problem is set up, what we should put on the initial line. Here's the way to think about this. Let's imagine that we had a beaker of, say, a liter of water, and we had enough calcium fluoride that we knew we were above the molar solubility. So we had more than 3.317 times 10 to the negative 4 moles of calcium fluoride in the bottom of this beaker. But somehow, maybe by putting a thin partition or something between the solid and the liquid, we were able to keep the solid and the liquid separate in the initial state, such that the initial state contained 0 dissolved Ca2 plus and 0 dissolved F minus. We then turn on dissolution by maybe removing that partition between the solid and liquid, and particles of CaF2 start to dissolve, forming aqueous Ca2 plus and aqueous F minus. This happens until we reach the molar solubility, until we reach the maximum number of moles that can be dissolved in that liter of water, which is 3.317 times 10 to the negative 4 moles. Based on the parameters of the problem, then, we already know what the equilibrium line is going to be, and we already know what the change is in this hypothetical process where we turn on dissolution. The change, considering we're, first of all, starting with a Q of 0, we're going to get Ca2 plus and F minus ions, and hopefully that should be intuitive. From the molar solubility, we can immediately write what the change is. 3.317 times 10 to the negative 4 moles per liter of Ca2 plus, and we'll get twice that for fluoride, so 2 times 3.317 times 10 to the negative 4 moles per liter. We get twice the moles per liter of fluoride because for every 1 molecule of CaF2 that dissolves, we get 2 F minus. Now we can write the equilibrium line simply by repeating the change line, right? The equilibrium line is 3.317 times 10 to the negative 4 for calcium 2 plus, and for fluoride it is twice this, which is 6.634 times 10 to the negative 4 moles per liter for fluoride. From here to calculate KSP, we need only write the form of the equilibrium expression and plug in these equilibrium concentrations. The form of the equilibrium expression includes the products, the concentration of aqueous Ca2 plus, times the concentration of F minus squared, since the stoichiometric coefficient on fluoride is 2 in the balanced chemical equation. And if you plug in 3.317 times 10 to the negative 4 for the calcium 2 plus concentration, and 6.634 times 10 to the negative 4 for the fluoride concentration, you arrive at a final KSP value of 1.46 times 10 to the negative 10. So in a sense, in problems like this, we were able to go right to the equilibrium line by converting this number of moles of CaF2 that can dissolve in a liter of water into moles of dissolved particles, moles of aqueous ions, Ca2+ and F-. That involves a stoichiometry calculation when the coefficients on the ions are not equal to 1. And honestly, I still like thinking of this in terms of an initial change equilibrium type of setup, where we start with, for example, a partition between the solid and liquid, and then to turn on equilibration, we remove that partition. This is analogous, for example, to the process of removing a partition separating two ideal gases, and it evokes this image of equilibration which we've seen before.